Oh, no, no. Okay. All right, can you guys hear me okay? Can you hear me, Shane?
Yes, sir.
Let's see, maybe my volume is down. Let's see what my volume is.
Yes, I can hear you.
Okay, yeah, my volume's down. Yeah. Okay. Very good. We'll get started in just 1 minute here. Let me see if I can pull up the oh, well, that's interesting. Let me share the screen. Let's see. See if I can do this, and then we will. Okay, so we'll go ahead and get started. So I'm doing this from UTSA because I have to be here for the Micro 1 course. We're passing out for to getting things started, and for that reason, I may shorten this one just a little bit. May not be quite a full 50 minutes, but it'll be close. And it's going to take me just a minute to get everything lined up here because I don't have any stuff at home. So I'm going to share my screen, and then I'm going to bring up hopefully the Blackboard, and let's see. So I want to log on, and why is it? Okay, I don't know, it's doing something weird. Okay, there we go, Blackboard. And we'll log on and see if Blackboard comes up. It was having trouble earlier. Oh, good. It looks like it's going to be okay. Okay. And we'll go into OA1. So, shoot, yeah, I don't have, oh, maybe I did put it on. Let's see. No, yeah, maybe I did. Yes, oh, perfect. Okay. But, you know, I think maybe I covered this. Yeah. Okay, so, all right. The one thing I didn't talk about, I'm going to go back and pick up now. All right, so let me do that right now. Okay, so I finished up, but I left off the concept of precision versus accuracy, and so I'm going to cover that right now. So let's do that again. I'm really already missing my 3 screens. All right, well, it's apparently not going. There it goes. Maybe. I don't know. It's not letting me edit this for some reason. Oh, I see. It's a protected view. Okay, now it will. I don't know why I did that. Okay, there we go. Okay, so I didn't cover precision versus accuracy, so I'm going to do that now. And and so this is a really, for engineers, this is an important concept. And you may have covered it elsewhere, but many times it doesn't get covered very well, and you still see people writing silly stuff. So we have precision, accuracy, and valid. So we talk about precision, and what that means is you're reading a sensor, an instrument of some kind, could just be a ruler, and precision tells you how accurately or how it's the ability to read the value to a certain number of decimal places consistently. So for instance, if you're reading something with high precision, that means that you can read it to a lot of decimal places, and every time you read it, you get, assuming that it's measuring the exact same thing, you get exactly the same number or exactly the same reading. In accuracy, what you're talking about there is how close your instrument is to giving you the real world value. All instruments have some built-in errors. For instance, let's say you had a ruler, but it wasn't a perfect ruler, and whoever laid it out made a mistake. In every inch, it was short by about an eighth of an inch. So every time you read something, depending on how many inches it was, if it's 10 inches, you're going to be off by 10/8 of an inch. So you're going to be off by 1 1/4 inches. And so that means your ruler is not very accurate. But if you could read it, let's say you could read it to a 1/16 of an inch, and every time you measured the same thing, you got the exact same reading, that would be very high precision, but you'd still, say if it was supposed to be about 10 inches or 10 inches, you'd still be measuring it. You'd be off, your accuracy would be bad. Precision would be good, your accuracy would be bad. So here's a little illustration that sort of shows kind of how that works. It's not perfect because this is a target, which is a little different than measuring something, but it gives you a good concept. So notice we have 4 targets. In this target, we have a very tight cluster, but it's nowhere near the bullseye. In this target, we're clustered nicely around the bullseye, but the cluster has it's spread out a fair amount. Here your cluster spread out a lot, and it's nowhere near the bullseye. And here you have a tight cluster, and it's right on the bullseye. So when we see this, we say our precision is good, but our accuracy is off. And it turns out this sensor that gives you this kind of reading is a good sensor. It just has to be calibrated. Whereas a sensor that gives you these readings, you can calibrate it. You can calibrate the sensor from this target to this target, but you're not going to do any better than this target, because the problem is the sensor has built-in random errors. Here you have a great set. You have a very precise and a very accurate, and this is what we call valid. It's both. All right, so let me go over that one more time because this is an important concept, and you can ask questions if you want. So in this case, we have high precision but poor accuracy. In this case, we have high precision and high accuracy. In this case, we have good accuracy because we're clustered around the target, around the bullseye. But we're spread out so that our precision is not good. Here we have bad precision and bad accuracy. All right, so hopefully you can sort those out in your head a little bit. Accuracy is how close you are to the actual truth. Precision is how consistently and accurately, or precisely and consistently, you can read your sensor essentially, or the sensor will give you the information your sensors gives you. How consistent and precise it is. Okay, all right. So that's valid. All right, I'm gonna I'm going to switch then. We're going to go to the next stuff here. And we want to talk about number systems. So I'm going to close this, I think. And then I want to go down to content. Okay. And then, boy, it's just really slow. And then, okay. And then, I think we're good. Let's remember, let me do this one. And then we also. All right, and then let me just check this out real quick. Sure, we go through this. Yeah, okay. So I'm gonna talk about binary math now, and this is very important because this is fundamental to the world of digital design. And the reason that it's fundamental to the world of digital design is that in our binary world, in our digital world, we have talked about one of our principles for dealing with high complexity is that we use consistency. And one of the consistent things we do, we restrict all of our signal values to either ones or zeros, or true or false. Now, in an actual physical device, we represent those ones and zeros of that true false designation with a voltage level. And those voltage levels do vary from device to device. In the old days, back when I was a graduate student, all of our devices ran at 5 volts. That was just the standard. Everything was 5 volts. But in the last, that was true for a really long time. But in the last maybe 15 years, we have started going to lower and lower voltages for our devices. And the reason we've done that is because, first off, if you one of the enemies of making denser and denser integrated circuits is heat, and eventually heat's one of your limiting constraints. So the problem with higher voltages is that it generates more heat because more current flows. And so as a result, using lower voltages decreases the heat and allows you to get greater density. That's why some of the really cutting edge chips are now running at less than 1 volt. So true would be 0.9 volts or whatever, and false would be something close to 0. Now we actually have a range we have to use, and there's often a range between the 0 and the 1 voltage levels that's not defined. And we really don't want voltages in that level because if we put those into our device, we may get unpredictable results, and it also may delay the time it takes for it to settle to one of the other values. So we really do like to keep our outputs in a fairly tight range where we've defined false as something close to 0 volts. Maybe say in a 5 volt device, we probably would go up to maybe 1.2 volts, and below would be 0. And anything over about 3.9 volts or 3.8 volts would be considered a 1, all the way up to 5 volts. But those ranges obviously get narrower as we use lower and lower voltages. In our microprocessor course, we run our microprocessor. We actually built in 2 different power supplies onto the board so that we could power it at 5 volts or 3.3 volts, because many of the peripheral devices we want to interface to are at 3.3 volts, and then many are at 5 volts. So that made it easy to just change the voltage that your board was operating at, and then you could easily interface it to your 3 or 5 volt part. Sometimes when you have mixed voltages in a system, then you have to have level translators, which translate from, say, 3.3 volts or 5 volts maybe to 1.8 volts, depending on what's going on. In in our digital systems design course, when we use a Xilinx FPGA, we can actually program our pins for a whole range of voltages. I think we can get down to something close to 1 volt, 1.8 volts, or 3.3 volts. I think those are the choices we can have. But the internal chip itself is running pretty much at something like less than a volt, or maybe 1.2 volts, I think, something like that. So, and again, we've gone to these lower voltages because of heat. All right, so because we have pretty much restricted all our signals to be either a 1 or a 0, true or false, based on some voltage level, depending on what voltage the device is running at. Binary math seems to make really good sense for representing our logic functions. And that's because in the binary world, we just have two values, 0 and 1. 0 is false and 1 is true. And so we've defined almost all of our binary devices, almost all of our digital design works using the concept that we're restricting our signals to true or false, 0s or 1s. And
Professor,
go ahead.
Are we supposed to be on a specific page on your screen? Because all I'm seeing is start of binary. I don't see any notes, or you just talking.
Yeah, I'm going to switch it in a second.
Okay. Just making sure.
Yeah.
Is the slide available for us to follow along, or
yeah,
you don't have it?
It's on Blackboard. It's under the old slides. I don't have my new slides with me because they're at home.
Okay, thank you, sir.
Yeah. So, but they'll be similar to these, but I'll populate those eventually. All right. So anyway, so that's why we use binary math. Okay. So now let's talk about number systems and number bases, because even though you've had this, you've probably been using the decimal system, but you probably haven't really thought about how it is formally defined. And so we're going to talk about binary or base 2 number systems. We're also going to talk about hexadecimal. I used to talk about octal, but it's not really important anymore because in the old days we had some computer instruction sets where octal made a lot of sense. But nowadays we don't really use that anymore. We pretty much just use decimal, base 2, and hexadecimal, which is base 16. And the reason that we use those 3 systems, first off, we obviously use decimal because that's what we learned. That's how you can, when you do math on paper or in your head, or even with a calculator, you're pretty much doing math in base 10. You really can't think in base 16. And although we'll teach you how to do a little bit of math in base 2, you're still really thinking in the decimal system. The reason that we like hexadecimal is because it has a special relationship to the binary system. And because of that special relationship, it's very useful to us. And I'll explain that a little more detailed in a minute. So as you go into your career, if you do anything in the digital world, you're going to use a lot of hexadecimal and a lot of binary. And obviously, you're still going to be stuck with the decimal system because that's where you've learned how to do all your math. So we're going to talk about the formal definitions of these. And like I said, I'm going to really skip through octal because that's one of the things I didn't really talk about octal in my new book, but in the old books they did. But there's no real point in it because it also has a special relationship to base 2, but it's just not used anymore. Okay, so here's base 10. Now, when we write a number in base 10, if we're writing in a bunch of different bases, then we normally write the base as a subscript at the end of the number. Here I have a subscript of 10 representing that this is a decimal number. Now, you know it's not a binary number because in the binary system, we only have 0s and 1s. It could be a hexadecimal number, though, because these are all legitimate digits in hexadecimal. So the only way you know is to have some particular designation of the base. So whenever you write a number, you need to know, it needs to be clear what base you're using. And that's going to be true for the remainder of your career because you're going to write numbers in binary, you're going to write numbers in hex, and you're going to write numbers in decimal. Now, the way this generally works in most of our computer-based tools is if you work in decimal, we usually don't have any indication. We just assume it's decimal if there's no other information. If you're writing in binary, we usually proceed it with a 0B, and then we put the number. Or if the number only has zeros and ones, you can kind of guess it's probably binary. In hex, we proceed it with a 0x, and the B and the X, the B for binary and the X for hex, can be lowercase or uppercase. Typically, they're not required to be one or the other necessarily. But I pretty much always use uppercase just to be consistent for hex, and I usually use lowercase for binary. I use a little b for binary and a capital X for hex. 0x, and then the number for hex. 0b, and then the zeros and ones for the binary number. All right, or you can use this subscript notation. It's not used except probably in textbooks, but in the real world, we don't really use that much. Okay, so if we have 953.78 base 10, what are those? How does this work? What are those digits? What do those symbols and their position really mean? Well, you may not have known it, but what it really means, we take the 9, and well, we start with the decimal point, and every symbol, again, we have 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Every symbol is multiplied by a power of 10, starting from the decimal point and working with positive power, starting with 10 to the 0 power, and 0 is a positive number. So 10 to the 0, so this 3 is multiplied by 10 to the 0, the 5 is multiplied by 10 to the first, and the 9 is multiplied by 10 to the second, as you can see here. So the 5 by 10 to the first, the 3 by 10 to the 0. Now, when we get to the decimal point and we go to the right side, we have to go with negative powers of 10. So the 7 is multiplied by 10 to the minus 1, or it's 7 times 1/10, or 7/10. And the 8 is 10 to the 2, or 100, so it's 800. So we have 8 times 10 to the minus 2, plus 7 times 10 to the minus 1, plus 3 times 10 to the 0, plus 5 times 10 to the 1, plus 9 times 10 to the 2. That's what these symbols actually mean. And when you add all these things up, you get 953.78. Now, you already know that because that's how you do binary, and you don't think about it in terms of these powers of 2. You just automatically know that's 900. That's 50. That's a 5 times 10, or 50. That's 3. That's 7/10, and that's 8/100. So you know that, but when you switch to another base, you might be confused. So let's look at the other bases. So here's the binary, and if we have a decimal point here, the decimal point would go right between these. So our basis, this 111.11, is 2 times 2 to the power. So 1 times 2 to the power of 3, 2 times 2 to the second power. 1 times 2 to the second power, 1 times 2 to the first power, 1 times 2 to the 0, 1 times 2 to the minus 1, and 1 times 2 to the minus 2. Well, so when we add all this up, so 2 cubed is 8, plus 4, plus 2, or plus 2, plus 2, then actually, sorry, 2 to the 0 power is 1. And then 1 times 1 is 1. So this 1 represents 8. This 1 represents 4. This 1 represents 2. This 1 represents 1. This 1 represents 1/2. This 1 represents 1/4. So if you add 1/2 and 1/4, you get 3/4, or 0.75. And if you add all these up, 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So this is 15 and 5/8. Is that what I said, or did I say 7/8? This is obviously, yeah, that's a half and that's a quarter. So if you put it in eighths, it's 7/8. If you put it in fourths, it's 3/4, but it's 0.75 regardless. All right, here's hexadecimal, same idea. We have A32. So because we need, now in hexadecimal, the base is 16. So in decimal, base 10, we have 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In base 2, we have 2 symbols, 0 and 1. In base 16, we have 16 symbols. We steal the numbers from that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but we're 6 symbols short because we need 16. So rather than create 6 brand new numeric symbols, they stole the first 6 letters of the alphabet. Now this actually was probably not the best idea in the world. The symbols were readily available, that's great, but the problem is we have capital A and lowercase a, we have capital B and lowercase b. So now we have to check when we look at a hex number, we have our numbers, when we type it in from the keyboard, it goes in ASCII values, which we'll talk about in a minute. ASCII values is a way of coding all our digits and numbers and special characters. But we have different ASCII symbols or different ASCII codes for a lowercase a and an uppercase a. So you have to search for both those. So when you write a routine to read in a hexadecimal number, you have to pay a little more attention to the fact that you could have an uppercase a or a lowercase a, and both would be a legal symbol in hexadecimal. So maybe one of these days somebody will create 6 additional symbols, and that's what we'll use for hex. But for now, we're stuck with the letters. So our 16 hex symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So we go all the way from A to F. Okay, and F, of course, is 15, A is 10. And so if you look at this, we use powers of 16. So we start, in this case, there's no fractional portion. So our 2 is 16 to the 0 power, or 2 to the 1, or 2. 2 times 1, or 2. 3 times 16. And then 10 times 16 squared. So we square 16 and multiply it by 10. We add to that 3 times 16, and we add to that 2 times 1, or just 2. And that gives us our number, which actually off the top of my head, I didn't do the math because I never can remember what 16 squared is. And this is octal, same thing, just to the base of the base 8. Now in this case, we only have symbols 0, 1, 2, 3, 4, 5, 6, 7. There is no symbol for 8 because your 8 symbols are 0, 1, 2, 3, 4, 5, 6, 7. But again, we're not going to use octal. We're basically going to ignore that because it's just fallen out of use so much that it's probably not important. Now, the reason why hex is so special is because when we represent numbers internally in the computer, we represent them in binary. But the problem with binary is, let's say we have a 32-bit number inside the computer in a register that's 32 bits wide. That's 32 zeros and ones. And it's very, very easy to make a mistake and get confused. And you have to sit there and count through those. So it's really, really hard to copy those numbers, to make sense out of those numbers, to figure out which bits where and all that. And so what we do instead, we convert those 32 binary digits, we convert those into 8 hex digits. And we do that because 4 binary bits exactly fit into 1 hex digit. So 4 binary digits fit exactly into 1 hex digit. And that's the special relationship. So here are the numbers above 10. So A is 10, B is 11, C is 12, D is 13, E is 14, and F stands for 15 in hex. So you need to keep that really straight in your mind. And this 15 is the same as 1111. So I think I have a list here. Let's see if I do. Yeah. So let's say we want to take. We want to write our hexadecimal digits in binary, or we have some binary digits we want to convert to hex. So all we have to do is group our binary digits starting from the decimal point, working first to the left, and then if there is a fractional portion, working to the right, and grouping our binary digits in groups of 4, and then translating each group of 4 into the appropriate hex digit. Now, the problem is we can't use decimal because it doesn't work. Because there's no exact number of binary bits that equal a single decimal digit. It just doesn't work. So, but it works great for hex, and that's why hex is very popular. One of the things you should do is go home tonight, and you should write down all the hex digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and write their decimal and their binary equivalents, just like this chart. Obviously, the decimal equivalents are pretty straightforward, just 0 through 15. But the binary equivalents can be a little confusing, and you should, really in the next week or so, you should make sure you've committed this to memory. I don't ask you to memorize much in this course, but this I want you to memorize. You should be able, off the top of your head, if somebody says, what is C, the hex digit C, what is that? What are the 4 binary bits that make that up? And you should be able to immediately know it's 1100. What is the binary for 7? You should know that's 0111. It's pretty easy to figure these out, but you should just have them memorized, and it'll save you a lot of time, and you're going to use it the rest of your entire career. And eventually you'll be forced to memorize it anyway someday, just because you're going to use it so much. But you might as well go ahead and learn it now, and then it will help. It will give you some facility with the course material to have this memorized. So I just encourage you, go ahead, commit it to memory. So write this down, and of course, you should obviously know what the binary equivalent is. All right, let's see. I think there's a. So, okay, let's go back here. So, I don't have my document camera here at school. So all I can do, so I can't really draw this out. On Monday, I'll work through some examples on paper, and it'll be a little bit more clear. But let's take this number right here. This one right here is sorry. It's 101000101101. Now, when you look at that, it's very hard to make sense out of that. It's just a lot of ones and zeros, and this is only 12 bits. When you get into 32 bits, it's really hard. So it's much easier to translate this into a hex number, and it's really easy to do it. I mean, I can do it on the fly. I can just look at it and I can go, it's A2D. That's what it is. I know that. But the way I do it, I start from the right side. Since there's no decimal point, then you assume the decimal point to be right here on the right side, and there's no fractional portion. And then you just divide this up into groups of 4. And I have a little video I made, a little animation to show you how to do this, and I'll play that for you Monday as well. But you group it in groups of 4, and then you translate it directly into the hex digit. So the first group would be 1101. Well, I already know from this table. We go back. Where is it? Oh, maybe it's ahead. Yeah, this is it. There. I already know from this table that 1101 right here is D. It's 13. 1101. And we know that's true because the first position is a 1, the next one's a 2, but it's a 0, so it doesn't count. The next one's a 4, and the next one's an 8, and they both are 1, so they do count. So it's 8.
Professor,
Go ahead.
it's kind of hard to hear you. I just didn't know if your speakers or your mic was causing some kind of interference.
Well, I'm just using the mic on the laptop. So, yeah, I don't know. Maybe I can. Maybe it's. I don't know. Maybe I can make it a little better. Let's see.
Yeah, that's better.
Yeah, I'll try and. I think the mic's actually on this side. I'll try and speak. Is that better?
Yes,
Yeah.
sir.
Okay, I'll try and talk over here. Maybe that'll work better. Okay, so in this case, we have 1101. Okay, so that's D or 13. So how do you know that's 13? Well, So if you look at the binary bits, remember they're 1, 2, 4, 8. This is 2 is a 0. We don't add that. So we have a 1 plus a 4 plus an 8. So that's 12 plus 1, 13. All right. And here we have 8 plus 4 plus 2 plus 1. So that's 15. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. All right, so you should just memorize this so you just know off the top of your head all these values. Okay, so we go back here. So the first group is 1101, and then we have 0100, or reading the other way, 0010. So if we go back and look at this, 0010 is 2. And then if we go back here, then the first group of 4 is 0101, and that's A. Right here, 1010, reading the other way, 0101. All right, so just memorize these and it'll be easy. Now, the question is, well, what happens if you don't have 4 bits? You pad with zeros, and you do that when you're at the decimal point working left, you pad with zeros on the left side. When you're working from the decimal point to the right, you pad with zeros to the right. And you can always put zeros on the left, and on the other side of the decimal point, you can always put zeros to the right. Okay, so that's the special relationship that hex has with binary. You can instantly translate. And so when we work with big binary numbers, we normally just in our head switch them to hex to make it a whole lot easier to work with them. And we'll show you a few other tricks. You can do the same thing with binary. You just group it in groups of 3, and each group of 3 binary digits directly maps to 1 octal digit. But again, it's pretty much fallen out of use. All right, one more topic, and then I'm going to wrap it up. So I want to talk about how we represent negative numbers. Now, it really helps if I can use pen and paper and draw on the board, but I don't really have that capability in my office here at work. So I'll when I do this, of course, in the classroom, we can, or when I lecture on Monday at home, I will definitely do this and show you.
Professor, you're breaking up again.
All right, sorry. Yeah, I have a really fancy mic at home, but I don't have one here, sorry. All right, well, anyway, so we're going to talk about representing negative numbers using binary numbers. It turns out there are 3 different ways that come to mind for, if you're a mathematician, you'd say, well, there's 3 different ways you can do this. Of the 3 ways, we only use really, in common usage, there's only one way that we use. And the other 2 ways we don't really use very much. So here are the 3 ways. One is called sign and magnitude. And the way this works is we designate one of our bits to be a sign bit, and then the other bits represent the magnitude of the number. Now, when I'm talking about now, I'm still talking about integers. I'm just talking about signed integers. So plus and minus integers. I'm not talking about so-called floating point numbers where we have fractional portions. When we use fractional numbers, we represent things using what's called the IEEE 754 standard. I'm not even going to explain it in this course because it's fairly complicated, but I do go over that in detail in the digital systems design course. But in this course, we're not going to really mess with floating point numbers. Everything we do in this course is going to basically be small binary numbers with no fractional portion. And when you get into the fractional portion, it opens up a big can of worms. It's very complicated to do multiplication and division with signed binary fractional numbers. And it's probably better just to leave that to experts who sweat bullets to write big routines to do this on your behalf, because it is pretty complicated. It's surprisingly complicated. But we do deal with signed positive and negative integers, and you do need to understand that. And the system we use for this is called 2's complement. But as I mentioned, there's also sign and magnitude is one system you could use, and 1's complement is another system you could use. But both of those have a problem. And the problem that they have is that they have both of those sine and magnitude and one's complement come up with two different representations for zero. Now, that doesn't sound like a problem, perhaps, but to a human, it's not. We're pretty flexible. We can roll with it. We can deal with that. But digital hardware doesn't like confusion like that, and so it really complicates a digital adder, digital subtractor, a digital multiplier to have two different representations for zero. Big problem. It turns out in 2's complement, we don't get that. We only have one representation for zero. And I will show you on Monday why that is. It pretty much has to be done on paper, so I'm not gonna try and explain it today. But what I am gonna go through is kind of tell you how these three systems exist and how we convert numbers from one to the other. Okay, so in one's complement, positive number. So in all three cases, both sine and magnitude, one's complement and 2's complement, we think in terms of the highest order bit, the bit on the left, that is always going to represent whether the number is positive or negative. In sine magnitude, that bit is specifically designated as a sine bit. In one's complement and 2's complement, it's not designated as a sine bit. It is part of the number. We have to use it in all our calculations, but it represents whether the number is positive or negative. So it effectively functions as a sine bit, even though it's not really a sine bit per se, but it works that way. So you can consider it as a sine bit, but it's still part of the number. So you can't leave it off.
I had a question, but I think I'm a little bit confused just to make sure. So on one side, the leftmost number is what's going to distinguish whether it's positive or negative?
That's right. So down here, you see these two numbers at the bottom that we have a number right here, n equals 0, 1, 0, 1, 1, 0, 0. The higher order bit is a 0. So that would be if that's considered a sine number, that would be a positive number. Over here, we have the higher order bit in these red digits is a 1. So that, if that's considered a sine number, then that would be a negative number.
Okay, so once that number is higher than the, okay, I think I get it.
Yeah, now remember, we can also, if you just look into the computer and you see some ones and zeros, do you know whether that's a signed number or whether that's an unsigned number or whether that's an ASCII code for an A or whether that's part of a picture? You're looking at 8 bits of a picture. You have no idea, right? So how would you know that? The only way you can know that is in the context of the software that's using that particular memory location. And that software has to be smart enough to know what that's supposed to be. So when you write a program, like when you write a program in C, you have to say whether when you create an integer, you have to say whether it's signed or unsigned. Now, if you don't say, it's considered signed. Now, what's the impact of that? Well, the impact of that is if you want to have, say your computer in C, integers are compiler specific. So you don't know how many bits an integer is unless you know which compiler you're using, because it depends on each compiler. They're allowed to have, some integers can be 16 bits, some can be 32, some could even be more than that in some computers and compilers. But for the most part, they're either 16 or 32. In most microprocessors, integers are 16, but sometimes they're 32. So you just have to know, and it varies. Well, when you look at that byte in the computer, you don't know. But when you look at your C program, you can see when you define, say the variable's X, okay? It's a 16-bit integer. Is it signed or unsigned? Well, when you declared it, you created it as either signed or unsigned. And if you didn't specify, by default, it's a signed integer, which means in 16 bits, you can go from 0 to 64,000 or 65 something, right? If you want to create a for loop and you want to run that for loop 40,000 times for some reason, but you create an integer j that's going to be your for loop index, and you let j be signed, the maximum size j can get to be is only 32,000. So your for loop's not going to ever run to 40,000. And it's not going to give you an error either. It's just going to stop working correctly. And you'll be pulling your hair out trying to figure out why your for loop can't go to 40,000. And that's because when you declared j, you declared it, maybe you just declared it as an integer. You didn't specify that it was supposed to be unsigned. By default, it became a signed integer. And by default, you can only fit up to 32,000 in 16 bits in a 16-bit signed integer. So that's why you can think of the higher order bit being a signed bit, because when you cross over, when you have, say, in 16 bits, you have 32,000 positive numbers, but you have 32,000 negative numbers. And all the negative numbers, that higher order bit will be a 1, and all the positive numbers, the higher order bit will be a 0. Now, how do you make a ones complement? A ones complement's easy. You just take every bit and flip it. So if n is, if a positive number n is here and you want to make it a ones complement negative number, you just flip every bit. And the formula for that is 2 to the n minus 1 minus the number. But it's the same as inverting every bit. All right, in 2's complement, it's a little different. We just subtract the number from, say, if we have n bits, we take 2 to the n minus the number. And that gives us the 2's complement. What we basically do is we flip every bit and we add 1. But another way to do that, and I typed it out here, you can form it by complementing every bit starting from the first bit to the right, and then starting from the first bit to the left of the first one. So take the number. So pay attention so you catch this. So there's an easy way for a human to do it, but there's a hard way but it's not an easy way for the computer. So the computer does it by flipping every bit and adding 1. Humans do it like this. We start at the right side, we copy bits until we get to the first one. We copy that, and then we flip every other bit. So if we start with this number here, 0, 1, 0, 1, 1, 0, 0, what we get for 2's complement is this over here. So only the red bits got flipped. We copy bits till we get to the first one, we copy that, and then we start flipping bits. And we always work from the right when we switch to 2's complement. And if you look at this, the value of this has nothing to do with it. It's a negative number in 2's complement, and it works correctly. But if you actually looked at this, it has an unsigned value that's much larger than the number that it really is. So we don't consider its unsigned value, we consider it 2's complement. So let's say I gave you this number, 1010100. I said, this is a 2's complement number in 7 bits. What's its value? What minus number does this actually represent? You would have to first convert it back to a positive number and then calculate its value. And if we do that, again, we can do it pretty easily. We start from this 0, that represents 1, but it's 0, so we don't add it. That's 2. That's 4. We do add that. That's 8. We add that. So now we have 12. That would be 16, but it's a 0. This would be 32. So now we have 32 plus 12, or it's 44. So this is the representation in 2's complement, 7 bits for minus 44. But it's very hard to look at that and know that. And the interesting thing, if we add these two together, we'll get 0. Now, it'll come out a little weird, because what you actually get is you may get an overflow, but your 7 bits will all be zeros. And in 2's complement math, we ignore overflows. Okay. So let me just explain. So the reason we use 2's complement, is because it makes the hardware for doing math inside the computer easier. When you were taking, math throughout your, course of study so far, you've used a plus sign and a minus sign to indicate positive and negative integers, or for that matter, positive and negative numbers, even fractional numbers. But we don't do that in the computer because in the computer, we don't have minus signs. What we do in the computer is we use 2's complement. And we use 2's complement because there's only one representation for 0. And it makes the hardware much simpler to build. So that's why we use 2's complement. We don't use sign and magnitude, except the IEEE 754 standard for floating point numbers does use sign magnitude. And we don't use 1's complement much at all. So I don't really push the 1's complement. You don't really have to know much about 1's complement. It's really just inverting every bit anyway, so it's pretty straightforward. But if you're talking about math, then you have end around carries and it's a little more complicated. So how do you know when you add 2's complement numbers whether or not you've overflowed? And the answer is very simple. You ignore, unlike with unsigned numbers where a carry out's very important, that means you overflowed. And maybe I should illustrate that. I'll draw this out for you on Monday and it'll be a lot clearer. But let's say we're going to work with 4 bits, okay? And so if all 4 bits are 1s, that would be 15, right? 1 1 1 1. You know that's hex digit of F. It's 15. So let's add 8 and 8, which should be 16. So if we add 8, which is 1 0 0 0, and another 8, which is 1 0 0 0, that's going to give us 1 0 0 0 0. 5 digits with the higher order digit being a 1 and all the rest being zeros. So if we actually did that in computer with a 4-bit register, with 2 4-bit registers, our final result in those 4-bit registers would be all zeros. So we added 8 plus 8 and we got 0. That doesn't make any sense, right? And that's because we couldn't fit the answer in the number of bits we provided for the answer. We overflowed. And overflowing is a big problem in computers. If you overflow, you get the wrong answer. So how do you know if you overflow when you add unsigned numbers, just where all the numbers are considered positive? You know that you overflowed because you need an extra bit to hold the result than the number of bits that you were using. And usually what happens in a computer, that goes into what's called the carry bit. So in the carry bit, when we have a carry out, which means the carry bit gets a bit put in it, that's an overflow when you're using unsigned numbers. But if you're using signed numbers, you ignore the carry bit. It doesn't tell you about an overflow. So how do you know if you have an overflow with signed numbers? And the answer to that is just what's on the chart. If you add 2 positive numbers and you get a negative result, that's impossible because 2 positive numbers have to still be positive. But if it turns out that the higher order bit is a 1, that means it's negative. It means it did not fit in the room you had. And if you add 2 negative numbers, then you can't get a positive result. So now what happens if you add a negative and a positive number? When you do signed addition with a negative and a positive number, you cannot overflow, assuming that you add the same number of bits to the same number of bits. So if you add 1 4-bit add-in to another 4-bit add-in, you have to get a 4-bit result if one's positive and one's negative. You can't get a 5-bit result. Okay, so in 2's complement math, we ignore the carries, but we must look at both add-ins and see if they were both positive. We have to check the result to make sure it is positive. And if it's not, we overflowed. Or if they're both negative, we have to check the result to make sure it's negative. And if it's positive, we overflowed. But if we had a positive and negative, then we know we don't have a problem. So we're good. Okay, I think I'm going to stop there. So I will pick back up on Monday, and I'll go back and I'll use paper and pen and draw most of the stuff out so it makes a little more sense. All right, I'll stop. Any questions about that?
Yes, are we gonna go over the one compliments and two compliments examples on Monday?
Yeah, I'll talk about the twos complement fairly extensively. I'm not going to talk much more about the ones complement because I'm not going to require you to know that.
Okay, so we just need to know two compliments.
That's all you really need to know. That's all that's really used. The ones complement is pretty simple anyway. You just flip every bit. But we don't do math with one complement. We do math with twos complement. That's just universally true. And there is some, like I said, the IEEE 754 standard for floating point numbers uses sign magnitude. So there is a little bit of sign magnitude, but sign magnitude is very straightforward. The higher order bit is the sign bit, and the rest of the bits are the value.
Okay,
I have a question also. Well, I guess I'm sure you've answered this before. I just want to clarify. The presentations can be found under content, correct?
Yeah. There's, if you look here, I think I've got it out. If you go into content, and then you scroll down at videos F21. There's the first Zoom class. There's the second Zoom class. I'll post this one right in. Okay.
Okay, sir. Thank you.
All right. Any other questions? All right. We will see you all later then. See you Monday. Have a good weekend. Be safe.